everyone. My name is Sindhuja, working as an assistant professor in the Department of Cybersecurity and Data Science, MLR Institute of Technology, Hyderabad. I welcome you all with another video on my subject called Stream Processing and Analytics. Today, my topic is Distributed Stream Processing. Okay, so we are going into the topic now. We are going into the subject now. So, the overview of today's presentation is distributed stream processing. How does it work and what are the benefits of using distributed stream processing? And as a second part, we are going to learn about stateful stream processing in a distributed system. So now let's go deep into the subject. The first part is that distributed stream processing. What does it mean? So distributed stream processing is a programming technique. We can say that it is a programming technique that processes continuous streams of data in real time. As I have told you that stream processing is nothing but we are analyzing or we are dealing with the continuous flow of data. So here we are distributing that continuous data among multiple devices. It is also known as event stream processing, data stream processing or stream analytics. So everything we can call it as data stream processing, distributed stream processing. So here we can see that what is distributed stream processing. So due to the complexity of work with a big data, often the solution lies within the distributed processing networks. Okay, here if we have big data in a larger amount, how can we work or analyze that kind of particular big data? So here this techniques comes as a solution for working with those type of complexity of workloads. So here the principle is that you spread larger and complex tasks over a number of computers or servers. Here the workload is distributed among multiple devices which are managed by one central system. So here if you can see in the diagram, there are multiple number of systems connected with one particular central node. This is nothing but distributed stream processing. Typically one computer will be allocated as a master. Okay, here the central system is allocated as a master and will control the others. So by using the central master system, we can control all other multiple systems. Each computer is allocated subtasks and messages and then passed between computers in order to meet the overall goals. Okay, so as data is distributed among multiple systems, each and every system will get some tasks which they have to perform. So this is nothing but we are distributing the workload among multiple systems, which is nothing but distributed stream processing, which follows programming techniques. So now let's move on to the next slide. So how does stream processing in a distributed system works? So use distributed architectures to process data from multiple sources. As I have told you that we are collecting the data from multiple sources. Okay, multiple sources to perform the analysis, right? So here we are following the distributed architecture. We are collecting data from source 1, source 2, source 3. This is how does distributed stream processing works. Now let's move on to the second point. Applies a series of operations to each element in a stream of data. As the data is distributed among multiple devices, so some set of operations are employed to that particular systems so that each and every element of that stream can perform and can analyze each and every individual elements. Can be used to detect conditions in data in real time. It can also used to detect the conditions in each data in real time. So what type of data and how much data is accumulated, everything we can detect by using this kind of technology. Then what are the main benefits of using distributed stream processing? So distributed stream processing increases efficiency. What does it mean? It increases the data processing efficiency and reliability of data processing, which means that we can believe and we can follow this technology. It will process within a short period of time. Can be used to develop scalable disaster recovery strategies. It can be used to scalable. What does scalable means here? Scalable is nothing but which can increase or enhance, right? The word meaning itself suggests that it is enhanced. As the data increases and the complexity of the data processing increases, it can use to develop that kind of scalable disaster recovery strategies, which we can collect the data as a recovery process. Allows for parallel processing of data streams. It can also allow parallel processing as the multiple systems are working in parallel, so it can allow parallel processing as well. Okay, now let's move on to the next slide. Okay, here as we are talking about stream processing, so here they have given a small difference between stream and batch processing. What is stream processing and what is batch processing, and how much data we can see in both the processing. One fundamental difference of stream processing within the MapReduce model is batch processing has the access to the complete data set. As I have told you that in a previous slide, batch processing is nothing but as a whole data is divided as batches, and by using some time intervals each and every data is going to process, right? So we can consider all the batches as a one whole data set, so we can have the access to, we can access the entire complete data set at once. Whereas with the streams we can see only a small portion of the data set at any time. We can have the small portion of data means as the data is distributed among multiple systems, each system has divided again the data into partition. Okay, the data into partition. That is the reason here only a small portion of amount of data we can see in a streams. To distribute the processing load among a series of executors. Okay, as here there is a technology called master executor technology works here. Okay, so as I've told you that this is the central system which controls the entire all the other systems. So this is nothing but master system we can call, and these are the executor machines. Executor 1, executor 2, executor 3 and executor 4. So all these executor works parallelly to perform or to get some insights. So as the data is distributed among these executors, we further split those data into partitions, partition 1, partition 2, by using some tools and technologies. So each executor get to see only a part of the complete stream. So here we get a chance to see only some portion of the data from each executor. That is the reason here it involves only small portion of the data only we can see in distributed stream processing, whereas in batch processing we can have a chance to access the entire data set at once. Now let's move on to the next topic. Then what is stateful stream processing in a distributed system? First of all, before going into the topic, we just look into what is stateful stream processing, then how it is going to implemented in distributed systems. What is stateful? Here the stateful, we can say that everything has some states and states, right? We can say in any process we can say that any state involves. So stateful stream processing involves managing and utilizing intermediate state information while processing continuous stream of data. Here state represents that, intermediate state represents that we are managing and utilizing some continuous flow of data as a whole. Here if the data is distributed among two systems in a continuous manner, we are here managing on, we are just saving some intermediate states. Intermediate states are nothing but the previous history of the data or previous transactions or interactions, we can say. Stateful processing retains context across events, enabling complex operations like aggregations, joins, pattern detections. Okay, here what is the use of storing that kind of state of every continuous data processing means those are helpful for the next processing or next operation. Suppose I'm just performing some operations here. So for that operation I want the output of the previous system output. Okay, I want here as an input, I want previous system's output. So here as a stateful process it will store my aggregate value for next batch processing or next stream processing. Why? Because as a whole, if we consider continuous flow of data which requires the past history as well, because to proceed with the next system or a next processing data, every system requires the previous data as well. So which is nothing but state, we can say that. Here in this diagram it is showing very detail. Okay, here we can say that as a data continuously flows from input to output, here stateless stream processing, it doesn't store or it doesn't manage any state here. While in stateful stream processing, it has storing some state. I mean, it is storing the intermediate storage or intermediate data for further analysis of the data. Now, distributed stateful stream processing frameworks, what is the meaning of framework? Okay, here framework is nothing but it is a set of rules. We can say set of rules which we have to follow, or a set of procedures which we can follow to perform some operations. So distributed stateful stream processing frameworks such as Apache Flink, Kafka, Streams and Samza provides the necessary tools and infrastructure to maintain state and process events in real-time data streams. In the real-time examples, we can say that Apache Flink is one of the framework which is provided for implementing distributed stream processing, and Kafka Streams. Okay, in a coming slides or coming sessions, we are going to learn about what is Kafka and what are the Kafka Streams. Those provide necessary tools. So which are the tools required to distribute the data among multiple systems, and what are the infrastructure requires? Those kind of infrastructure it provides to the distributed stateful processes. Okay, these frameworks, the above mentioned frameworks, enable developers, those are helpful for developers to build robust and scalable applications. Robust means which are very perfectly built, and scalable applications. Scalable are when the data increases, that kind of data also easily managed by these frameworks because of streams that can handle large volumes of data and make timely decisions based on the incoming streams of events. When the data comes generated on a continuous basis, so these frameworks can have the capability of storing that kind of data and perform easily by using this kind of frameworks like Apache Flink, Kafka and Samza. Okay, now what are the applications of stateful stream processing? At what places we are going to use this kind of technology or processing systems? Okay, especially we are going to follow this kind of applications in personalization, fraud detection, and supply chain management. Personalization means it is related to some social media or social media apps. How does it related to social media? Here we are going to see stateful stream processing can be used to provide personalized experiences for users based on their past interactions and preferences. Suppose if any person uses social media or e-commerce website, if they search for any product, there may be chances of storing their previous history based on their interactions and previous preferences. There is a chance of recommendations. Okay, personalized recommendations for future purchases or future product recommendations. So in that kind of technologies, this kind of stateful processing helps them a lot to grow their businesses. And fraud detection, it compares with a bank. It is related to banks. Okay, stateful stream processing can be used to detect fraudulent activities in real time by tracking changes in the state of a system over time. Okay, here every transaction has some specific time, right? So those time are tracked via multiple systems over time. So this stateful stream processing can help them to detect fraudulent activities in real time. So if every time the transaction time changes, so there may be chances of storing stateful stream processing, so we can detect those kind of fraudulent activities of any other hackers. Next, supply chain management. Okay, supply chain management is related to goods and services. Okay, stateful stream processing can be used to track the movement of the goods. Okay, here it is related to goods through a supply chain in real time. Okay, as we can compare with our previous storage or inventory of the goods, and to make informed decisions about how to optimize the flow of goods based on the past data. Okay, how to optimize the flow of the goods. As the company involves in a inventory, there may be chances of predicting the next goods of that company or that supply chain, so that stateful stream processing can store its previous history or past data to predict the future usage of that particular good or any other products. Okay, These three are the main applications where stateful stream processing can help them to grow their benefits. Okay. Now let's move on to the challenges of stateful stream processing. So here, what are the challenges we face while working with the stateful stream processing are, as already the data is huge, right? So we are making additional burden. We can say that here we are posing additional burden to the system. Why? Because already the data is huge. Here, by storing the intermediate state, additionally we are making the system on to handle another workloads, right? Each and every state. So we need to ensure that the state is preserved over time. So we have to make sure that each and every state has to be preserved over time based on their time and that processing time. We require data consistency guarantee, as the data is flowing in continuous format. So we have to make sure that data has to be consistently flowing from a source to destination, even in the event of partial system failures. So as the data is continuously flowing, there may be chances of failure in the systems as well. So these two are the two challenges we face while processing with the stateful stream processing. Why? Because we are making them additional burden to the system which is computing the continuous data. So thank you so much for your time and attention. Thank you.